Good morning, everyone. So today's theorem is Riemann's theorem, which is based on the rearrangement of the terms of real numbers. In the last video, we have discussed the rearrangement of the real numbers. The concept for this theorem is based on that only. So let's start with this theorem. First of all, there are some remarks we have to revise them. These are very useful in proving this theorem. First one is, a convergent series is said to converge conditionally if it fails to converge absolutely. So the series which converge conditionally, that will not converge absolutely. Second is, every absolutely convergent series is convergent. But on the other way, it's not true. May or may not true. So the convergent series need not be absolutely convergent, but an absolutely convergent series is convergent. Third, the series is conditionally convergent if and only if it is convergent, right? And the series of its positive terms diverges to plus infinity, and the series of the negative terms diverges to minus infinity. Then is, if summation an and summation bn, suppose these are the two series and both converges, then their sum also converges. Fifth, if we having this summation on an minus bn, this sum will open as summation an minus summation bn. This will true, or this will open like this only if one of them is convergent or both are convergent. If a and b and both are convergent, this is the case when this summation is open like this, or one of them is convergent. Either an is convergent or bn is convergent. If an is convergent, then bn must be divergent, or vice versa. So let's start with the theorem. Let summation an, where n going from 1 to infinity, be a conditionally convergent series with real valued terms. Let x and y be given real numbers in the closed interval minus infinity to infinity with x less than equal to y. Then there exists a rearrangement summation bn and going from 1 to infinity of this summation an, such that if we take the infimum for Tn, where limit goes to n goes to infinity, that will comes out to be x, and if we take the supremum on Tn for limit n tends to infinity, that will be comes out to be y. And what is Tn? Tn is first n terms summation. That means b1 plus b2 plus b3 plus b4 up to bn. Sum of the first n terms of bn, right? So we have to prove that the rearrangement summation bn of summation an, this rearrangement also exists with these two conditions, right? So let's start with the theorem, the proof. I'm taking small pn to be equal to mod an plus an by 2, and taking the small qn to be equal to mod an minus an by 2 for n belonging to the natural number, then this pn will be greater than equal to 0 and qn is also greater than equal to 0. And what is pn minus qn? If you subtract these two, what you will get? We will get an. And if we add these two, pn plus qn, this will comes out to be mod an. Fine. Now what about the series summation pn and summation qn? They diverge or converge? They must diverge, because if both were convergent, let's check what will happen. Suppose I have taken in the first part the sum pn plus qn, and this sum comes out to be mod an. And suppose we are saying pn and qn both are convergent, that means their sum is also convergent. Sum convergent means mod an is convergent. But it is contrary to the hypothesis what is given to us that this series summation an is conditionally convergent. And a conditionally convergent series need not be absolutely convergent, right? So, Pn and Qn must not converge, right? They must both diverge, because if they are convergent, then we are getting the convergent absolutely series. That is contrary to our hypothesis. So both must diverge. And if in the second part I take finite sum, that is n going from 1 to capital N on an, this will be equal to, what is an? Pn minus Qn, right? This sum, the difference will open like this, and what is the condition to open them? Either both are convergent or one of them is convergent. Pn and Qn, just now we have seen that these are divergent series. So we cannot take that these two are convergent. The other thing we will take, the summation is open if one of them is convergent. So therefore, divergence of summation Pn and convergence of summation Qn, or you can also say divergence of summation Qn and convergence of summation Pn, implies divergence of summation An, which is again contrary to our hypothesis. Because whenever one of the series is convergent or divergent, then the resulting series is An. That resulting series will be divergent, which is again contrary to our hypothesis, right? Okay. So now I have taken capital P1, capital P2, capital P3. Let this P1, P2, P3 denote the positive terms of summation An in order in which they occur. And let Q1, Q2, Q3, these denote the absolute values of negative terms for summation An, also in their original order. See, Q1, Q2, Q3 is the absolute values of the negative terms. So, because these are the absolute values of the negative terms, so Q1, Q2, Q3 is also positive, right? So, I have mentioning this P1, P2 and Q1, Q2. And now, again, let's check. Pn will be equal to An when? If An is strictly greater than 0. How come? Let's check. See, this Pn will be equal to An if An is strictly positive, because if An is strictly greater than 0, then this will comes out to be An. And if this mod An, if An is negative, that means this will be cancel each other, so Pn will be 0 for negative values of An. Similarly, in the case of Qn, when Qn will be equal to An if An is less than equal to 0, right? And when Qn is equal to 0, Qn will be equal to minus An if An is negative, right? Then mod will also be negative. For An less than equal to, strictly less than 0, this mod is negative. You know this? So whenever An is strictly less than 0, the value will be minus of An. And this Q1 equal to 0, if this An is greater than equal to 0, then the value comes out to be An, and that cancel each other, Q1 will become 0. If An is negative, strictly less than 0, then this mod An changes to minus of An, and we will be getting Q1 to be equal to minus An, right? Hence Pn equal to An if An is positive, 0 if An is less than equal to 0, Qn is minus An if An is less than 0, and it is 0 if An is greater than equal to 0. Now since the series summation Pn and summation Qn differs from this Pn and Qn, their sum only by 0 terms, there is no difference. Pn is summation of the positive terms, and small pn also contains the positive terms. summation Qn, it is the summation Qn, we have taken the absolute values of the negative terms, and Qn contains the negative terms, right? So if small pn and small qn both diverges, then summation capital Pn and summation capital Qn are also divergent, as they do not differ from as they differs from the zero terms, one and the same. Now the construction part. Now we have to construct the sequence. We have to rearrange the terms of summation an now. So construct the sequence mn and kn such that the series. Just listen carefully. This is very important, how to construct the sequence. I am taking first k1 terms of positive terms, followed by first m1 terms of the negative terms, that is the absolute values. Then again followed by next k1 plus k1 up to k2 terms of positive terms, followed by next m2 terms for qn's, right? Here it is stopped with m1 and I continue with m1 plus 1 up to m2, right? Then next will be it stopped with k2, then I should write pk2 plus 1 up to pk3, then followed by negative. Such type of arrangement we have to make. So this is clearly a rearrangement of summation an which satisfies star. What is star? Star, I have mentioned in the theorem. Star is the taking the infimum on Tn will be x, taking supremum of Tn will be y. This I have taken to be as a star. So I have arranged the sequence in such a way which clearly is a rearrangement of summation and that satisfies star, right? Now the second construction. We have to construct two sequences of real numbers, say xn and yn, such that limit n tends to infinity xn equal to x, limit n tends to infinity yn equal to y, with xn strictly less than yn, where y1 is greater than 0. Because it is also given that we are having the real numbers x and y between in the closed interval minus infinity to infinity, where x is less than y. That's why we have constructed these two sequences. We just enough say k1 positive terms so that pick up your k1 positive terms and make them greater than y1, right? See how to remember this. If you are ending up with the positive terms and having the subscript k1, just write this is greater than y, because here it is 1 for k, so you write here y1. Followed by just enough say m1 negative terms, so that now adding these two m1 negative terms. And if you are ending up with these negative terms, I use red color for the negative terms and orange color for the positive terms. If you are ending up with these negative terms, then here subscript is m1. Write this for x1. This is less than x1. See, if you are ending up with the negative terms, write the sign as less than. If you are ending up with the positive terms, write the sign greater than. Okay, for positive terms use y, for negative terms use x. Again, now I have to add positive terms to this inequality. So I have added pk plus 1 up to pk2. More positive terms I have added. So because I am ending up with the positive terms, I must write y with subscript 2 and make the sign greater, right? Again followed by the more m2 negative terms. So because I am ending up with the negative terms, I must write less than and with x2, because subscript is m2 here. So I should write x2 here. So these steps are possible because summation Pn and summation Qn are both divergent series of positive terms, right? So if the process is continued in this way, then we obviously obtain the rearrangement of summation Bn of summation An, which is given by 1. What we have marked 1? We have marked this rearrangement as 1. Now suppose take your alpha n and beta n that denotes the partial sums of 1 whose last terms are pkn and qmn. For alpha n last term is pkn. For beta n I take the last term as qmn. So since pkn is the last term for alpha n, last term of the partial sums of 1, so I taking all the positive terms up to k1 followed by the negative terms, then positive terms, and reach pkn, the last term. And I have to write, because I have ended up with the positive terms, I must write yn with greater than sign. And because it is a partial sum of our rearrangement and it denoted by alpha n. So last term is pkn, I do not hold this as alpha n. If I remove this last term, then this sum will be less than equal to yn, obviously, because this is your positive term, and with the addition of this positive term, the sign is greater than yn. Suppose I remove this positive term, then sign will change to less than equal to 1, because one term is removed from this sum. So this sum will be now less than equal to yn. Right? Now I just add again this pkn on both the sides, just to get the knowledge of this inequality sign, and I have added this additional step so that it will be clear with you by steps. So let's add this pkn on both the sides. So I'm adding this, which implies p1 pk1 minus q1 up to pkn minus 1. This we are having. Okay, let's add this pkn again on both the sides. Now again, what is all this sum? Because ends up with last term is pkn, this whole I write now as alpha n less than equal to yn plus pkn, right? Taking yn to the other side, this is pkn. Sorry, it must look as the subscript. Taking the mod, which is less than equal to pkn, as alpha n is greater than yn. So I can use mod here because alpha n is greater than yn, and also pkn is positive. That's why I can use now mod here. So similarly, if I obtain this inequality for alpha n, similarly I can reach beta n minus xn, which is less than equal to qmn. Fine. Now since summation an is convergent, because it is given that summation an is conditionally convergent, so obviously any conditionally convergent sequence is convergent. So because it is convergent, I am using the definition for convergent. En tends to 0 as n tends to infinity. This is the definition for convergent, which implies Pn tends to 0 and Qn tends to 0 as n tends to infinity. Why I have write this? Because an are the terms of this Pn and Qn, because an denotes the terms of Pn and Qn, the positive terms and the negative terms, right? These are nothing but the terms of an. So if Pn tending to 0 and Qn tending to 0 as n tends to infinity, this will also imply Pkn tends to 0 and Qmn tends to 0 as n tends to infinity. Nothing but the rearrangement of the terms. Okay. See, Pkn is tending to 0 as n tends to infinity. That means for given epsilon positive, there exists a positive integer n1 such that this mod Pkn is strictly less than epsilon by 2. I choose my epsilon to be as epsilon by 2 for n greater than equal to n1. Again, since we are also having yn tending to y as n tends to infinity, so there exists a positive integer n2 such that mod yn minus y is less than epsilon by 2 for n greater than equal to n2. I collect this and this. Now taking capital N to be the maximum for n1 and n2, then mod of alpha n minus y will be equal to, this will be equal to alpha n. Because I'm having yn over here, I have to use this mod. So I add and subtract yn like this, right? Which is less than equal to mod alpha n minus yn plus mod yn minus y, which is further less than equal to, because we know that alpha n minus yn mod, this is less than equal to mod pkn. See, alpha n minus yn mod, this is less than equal to pkn. So can I write here less than equal to for this pkn? Yes. And this mod yn minus y, this is less than epsilon, no, right, wait, this is further less than, pkn is less than epsilon by 2 because I have to use these two. See, for pkn I got this, for yn minus y mod I got this. So this is epsilon by 2 and this is also less than epsilon by 2, which is equal to epsilon for n greater than equal to capital N. Right? Thus, mod alpha n minus y, this is less than epsilon. Right? What is coming with us? This mod alpha n minus y. This mod alpha n minus y finally is less than this epsilon for n greater than n. But epsilon was arbitrary, so alpha n is tending to y. Similarly, by the same argument, we can prove that beta n is tending to x. So finally, it is clear that no number less than x or greater than y can be subsequential limit of the partial sums of 1. Right? Because these are tending to y and beta n tending to x. This is nothing but your subsequential limit because it is tending to some number. So, no number less than x or greater than y can be the subsequential limit of the partial sums. So, y is a supremum and x is the infimum. So, therefore, if 1 is denoted by summation bn, then 1 is what? The rearrangement. And I denote that rearrangement to be as summation bn. Then, if you take the infimum on Tn, this will comes out to be x, and supremum for Tn is y, where Tn is your b1 plus b2 up to bn. Right? It is proved now? Okay. This is an interesting theorem, and proof is also interesting. If you go through this proof 1 or 2 times, definitely you will remember all the steps. This is another theorem which is also very interesting. But here summation an is given to be as converges absolutely. In the Riemann theorem, it is conditionally convergent. In this theorem, it is absolutely convergent. So if summation an converges absolutely, then every subseries summation bn also converges absolutely. Moreover, we have mod summation bn less than equal to summation of mod bn less than equal to summation of mod an. Don't worry, proof is in just 4 to 5 steps. Not so long. So let's start with the proof. I have to mention this mapping f from n to n be 1, 1. Function. Right? And for given n, let n be the largest integer in the set. So let's form our set. See, f is a mapping from n to n. If I take the 1 here, so I will get the value f of 1 in here. Then for if I take 2, I get f of 2 in this codomain now. This is your domain, this is your codomain. So what will be there in my codomain? F of 1. If I apply f on 2, I will get f of 2 here, right? Then f of 3 up to fn. And capital N be the largest integer in this set, because f of 1 is nothing but any natural number, suppose n1. f2 is nothing but any natural number, suppose n2, right? Because codomain is a set of natural number. Whatever be the value over here, whatever be the value for you apply f, you get f of 1 as a natural number in codomain, right? So f1, f2, f3, fn, these are nothing but the natural numbers only. And taking capital N to be the largest of this set, right? Then I'm taking this summation, because this summation is from 1 to infinity. Let me take partial summation from 1 to n on bk, right? This is less than equal to summation k going from 1 to n mod of bk. Fine. This is less than equal to summation k going from 1 to, let's take infinity. Yes, tell me, guess. Obviously, this bk is a subseries for summation an, right? It is a subseries. So it's written here, if summation an converges absolutely, then every subseries summation bn. Because it is a subseries, so this is less than equal to the main series. Right? Okay. Now letting n tends to, because here mod of bn I'm having the infinity. So let's take here also I'm having the mod bk. So let's take infinity limit. So letting n tends to infinity. So make this to infinity. Summation bk. Now this k will not going from 1 to n but going to 1 to infinity. Less than equal to summation k going from 1 to infinity mod of bk. And this is as it is, because there is no n. Right? Now since summation k going from 1 to infinity mod bk, see these two, this is less than equal to summation k going from 1 to infinity mod ak, right? Now from this previous step I take this last one, these two, okay? Now the mod is less than equal to this mod, and we know that it is given that mod AK, this AK is conditionally convergent, right? So, sorry, I'm very sorry, it is absolutely convergent. What is given to us? That this mod AK is absolutely convergent. See, summation AN converges absolutely. So, and K going from 1 to infinity, mod AK is convergent. Therefore, by comparison test, summation BK mod also converges. K going from 1 to infinity, mod BK, this also converges. Thus, that's it. Summation n going from 1 to infinity, Bn converges absolutely. Fine. This is how we prove the series to be absolutely convergent. Right, so we use comparison test to prove this series to be converges absolutely. Right, simple steps. Okay, so thank you for watching this video. In the next video I must be going to start continuity, so let's get ready for that continuity topic. So thank you, God bless you, have a very beautiful, enjoyable, lovely day. Goodbye.